Hello students, after looking in detail with SN1 and SN2 mechanisms, we need to understand a concept called as stereochemical aspects of nucleophilic substitution reactions. As I have told, SN1 reaction proceeds with racemization, that is, the product is a racemic mixture, whereas SN2 reaction mechanism proceeds by complete stereochemical inversion, which is called as Walden inversion. To understand this concept, you need to know the meaning of the term stereoisomerism. Isomerism is of two types, structural isomerism and stereoisomerism. Now in stereoisomerism, once again there are two types. One is geometrical isomerism, about which you have studied in the previous class. And the second type is called as optical isomerism. Now this optical isomerism is a type of stereoisomerism which is exhibited by certain samples of organic compounds which are optically active. Not all organic compounds are optically active. A few organic compounds have the ability to rotate plane polarized light. Such samples are said to be optically active and they exist in two isomeric forms. So one of the isomer will be plus isomer, the other isomer will be minus isomer, about which you will know later. So an organic compound which is optically active exists in two isomeric forms and rotates the plane polarized light in opposite directions. These are called as optical isomers and the phenomenon is called as optical isomerism. Now after knowing the definition of optical isomerism, you should know what is this plane polarized light. If you take ordinary light from electric bulb, it has waves vibrating in many different planes. When such light is passed through Nicol prism, which is made of calcite is crystalline form of calcium carbonate, or Polaroid lens, the resulting light will have waves vibrating in a single plane. Such a light is said to be plane polarized light. An optically active organic compound will rotate the plane polarized light either in the clockwise direction or in the anti-clockwise direction. Now you should know the meaning of two terms, dextrorotatory and levorotatory compounds. The meaning of the term, D and L, small d and small l are the symbols used. So an optically active organic compound which rotates the plane polarized light in the clockwise direction, it is said to be dextrorotatory or D compound. Now this term dextrorotatory comes from the Latin term dexter, which means right. It is indicated by the sign plus written in brackets. So that is D compound or dextrorotatory compound. Whereas the optically active isomer which rotates the plane polarized light in the anti-clockwise direction is said to be levorotatory compound or L compound. It is represented by the sign minus written in brackets. So you should remember what are D and L compounds. Both are optically active. D compound is indicated by plus sign, L compound by minus sign. And this magnitude of rotation of plane polarized light is measured in terms of degrees. Either if it is a plus dash isomer, it will be plus, for example, plus 20 degrees, and the other isomer will be minus dash minus 20 degrees, in that way. Now if you take an equimolar mixture of the two, that is plus dash compound and minus dash compound, so that equimolar mixture of D and L compound is called as racemic mixture. It is optically inactive for the simple reason both the rotations, one being positive, the other being negative, cancel each other. Hence racemic mixture is optically inactive. Now this optical activity of a compound is measured, identified, detected by using an instrument called as polarimeter. So this is in brief which you should know regarding stereoisomerism. Now another important concept which you need to know is about a term called as chirality, asymmetry or dissymmetry. All mean the same. The meaning of the three terms is same. Either it is chirality or asymmetry or dissymmetry. All the three mean the same. Now before telling the details of this concept chirality, you should know what do you mean by a plane of symmetry. A plane which divides an object into two symmetrical halves is said to be a plane of symmetry. For example, if you take a hat and split it midway, it will have a plane of symmetry. Whereas if you take a person's hand, either your right hand or left hand, imagine to split it in between, do you get identical fingers on either sides? No. Therefore, a hand does not have a plane of symmetry. Such objects are said to be dissymmetric or asymmetric or chiral objects. This is with reference to objects. Later on I'll tell about the organic molecules. Such objects, if you place one above the other, they cannot be superimposed. Placing your right hand over the left hand will clash the thumb and the little finger. Therefore, they do not have a plane of symmetry. They are said to be non-superimposable mirror images. They are said to be non-superimposable mirror images. Remember this word. Chiral molecules are forming non-superimposable mirror image forms. The two will not be identical. Now coming to what do you mean by a chiral organic molecule. Now look to this example of 2,3-dihydroxy-1-propanoic acid. Yes. So 2,3-dihydroxy-1-propanoic acid. I have indicated the second carbon atom by means of a star. That indicates it is a chiral carbon atom. A simple way to identify a chiral carbon atom. A carbon atom bonded to four other groups, four different groups in particular, is said to be a chiral carbon atom, and a molecule which contains at least one chiral carbon atom is said to be a chiral molecule. Now if you place this molecule, imagine in front of a mirror. Just look there, you will get the reverse structure. C2OH, which was in the front, comes behind in the mirror image form. So the mirror image also contains a chiral carbon. These two are non-superimposable, placing one over the other structure. H and OH will clash, which are different groups. Therefore, they are non-superimposable mirror image forms. So optical isomers are constituted by a molecule and its mirror image, which have different arrangements in space, three-dimensional arrangements. If one isomer is dextrorotatory, then the corresponding mirror image will be levorotatory, that is D and L compound. Now these stereoisomers, which are non-superimposable mirror images, are called as enantiomers. So enantiomers are a pair of optically active non-superimposable mirror image forms. They are called as enantiomers. So chiral molecules do not have a plane of symmetry. They contain at least one carbon atom which is chiral or asymmetric or dissymmetric in their structure. Now coming to stereochemistry of optically active halides. Two halides, one for SN1 mechanism, the other for SN2 mechanism. So at first I will take SN2 reaction of an optically active halide. The example taken is that of 2-bromo-octane. The structure is written in the short form. Only the second asymmetric carbon is shown. You can extend the carbon chain C6 each time by the methylene groups. So this is the structure of 2-bromo-octane written in 3 dimensions. Now this 2-bromo-octane has C2 which is optically active. When this is allowed to react with sodium hydroxide or aqueous potassium hydroxide, the product formed will have the hydroxy group bonded to the back side of the leaving group Br minus at the asymmetric carbon atom C2, which is chiral carbon atom, giving the product as plus dash octane 2-ol. So therefore there is inversion of configuration. You have started with minus dash 2-bromo-octane and the product obtained is plus dash octane 2-ol. So if the reactant taken is alkyl halide is levorotatory, you will get the alcohol as dextrorotatory here. So this is regarding the stereochemistry of SN2 reaction mechanism. Only one example is mentioned for you all. Now coming to SN1 reaction of optically active halides. For SN1 reaction of optically active halides, the example taken is that of anyone you can take, either plus dash or minus dash. It should be optically active. Here it is 2-bromobutane. 2-bromobutane. So this is the second carbon atom which is optically active, or chiral carbon atom to which the halide is bonded, Br. So 2-bromobutane which is optically active, here it is plus dash isomer, undergoes slow ionization to form an intermediate planar carbocation in which the chiral carbon atom carries a positive charge and eliminating Br minus which is the halide. So this is the slow step, and the second step. In the second step, since the intermediate carbocation is planar, the chiral carbon atom can be attacked equally from the front side and the back side. If front side attack takes place, the product formed will be minus dash butane 2-ol, which has OH group at the same place where Br was present. If OH minus attacks from the back side, then the OH minus will form bond with the chiral carbon atom opposite to the position of the leaving group Br minus. So in the product formed, equal amounts of plus dash butane 2-ol and minus dash butane 2-ol is present. That is 50% of plus dash butane 2-ol and 50% of minus dash butane 2-ol. Therefore it will be an equimolar mixture. Hence it is called as a racemic mixture. This is what I wanted to tell you, the meaning of the term racemic mixture. And this mixture will be optically inactive. So this is the example to explain SN1 reaction mechanism of optically active halides. One example each for SN2 and SN1 is given, and this is more than sufficient for you all. So kindly remember these examples in detail. Yes, so here we will be completing haloalkanes. Now let us move to haloarenes.